Hi everyone, this is going to be the week 6 worksheet solutions. So for exercise 1, we want to evaluate the derivative of a particular integral. So this is something that we can do because of the fundamental calculus theorem. So if you remember, when we consider f of x being the integral of a to x of f of t dt, this is a small f, then f prime is going to be pretty much the function that is inside, plug in the limit times the derivative of this limit, which is 1 in this case, minus, of course, f of a, then the derivative of the limit, which is 0. So essentially, this is just going to be f of x. And that's why the fundamental calculus theorem gives me this. However, in this scenario, because the function that we're taking has two limits that are functions, then the derivative of this is going to be the cosine plug in sine of x times the derivative of sine of x, which is cosine of x, and then minus the cosine plug in x squared times 2x. And that pretty much is just the solution to this question. There's no way to simplify or to do anything else in here, so that's pretty much it. Now, question number 2, we have information on the sum of two integrals. We have certain information on the integral of f from 0 to 4 and from 4 to 2 of minus 2. So we want to know what the integral from 0 to 2 of g of x is. And so the key of this is to actually work out and find a way of subtracting the information that we have from here. So for example, if we can think of this, we can see the integral of g of x as the integral from 0 to 4 of f of x plus g of x, right? Minus the integral to 4 of f of x, because notice that we're pretty much get rid of f of x here, of the integral of f of x. Since this is equals this integral by properties of the integral is just this. Since this is just this, then we're pretty much and essentially saying, hey, I can cancel out, and now I have the integral from 0 to 4, but I don't need 0 to 4. I only need 0 to 2. So that means that I gotta get rid of the piece from 2 to 4. So this means that I gotta subtract the integral from 2 to 4 of g of x dx. But now, notice that if I have this sign by properties of the sign, this is equal to just the integral from 2 to 4, from 4 to 2 of g of x. I can kind of flip around with this minus sign. I can flip the order of the integral points. And so the good thing about that is that I'm going to have information about all these things. I have the information about this. This is minus 2. I'm going to have information about this one. This is 3. And I'm going to have information about this whole thing, which is 5. So at the end, this is 5 minus 5, and it's going to be just 0. Again, notice that the important thing is that I'm able to write the integral from 0 to 2 as a subtraction of different elements in here with the information that I have given. All right, let's transition to exercise 3. In exercise 3, we have the integral from cosine of 3x times sine of 3x dx, and this is clearly a substitution. The substitution is going to take sine of 3x as u. So u is sine of 3x, and so the du is of course going to be cosine of 3x times 3 because of the chain rule here, and this is the u dx, so du is 3 cosine of 3x dx, or you can think of this as the u over 3 is cosine of 3x dx. And so this integral here can be just seen as sine cube of 3x times cosine of 3x dx. And then you can see that this is replaceable by the u over 3, and this is going to be replaceable by u cubed. So this means that this is the integral of u cubed over 3 du. And this is just 1/3 of u to the 4 over 4 plus c. And this is just u to the 4 plus 12, or over 12, sorry, plus c. And then we replace to the original variable. And so this will be sine to the 4th of 3x. Okay? All right, so now let's go to exercise number 4. Notice in exercise number 4, we have the integral x minus 2 to the cube. X plus 1 over x minus 2 to the cube. And this seems to be something that I could do by substitution, because this x minus 2 over below is something that is kind of awkward, so it will be good to simplify it into a power. So if I get u is equals x minus 2, then the u is going to be dx, and the substitution is very easy to make, at least in the bottom. We get u cubed. Now the issue is the top, but we can replace that from here. So if we relate u plus 2 is equals to x, so if I just add 1 on both sides, I'm going to get that x plus 2 is just equals to u plus 3. And that is the relationship here. So now I get something that is much more manageable, and I can split this into integral. U over u cubed plus 1 over u cubed du. And this is the integral of u to the minus 2. And this is the integral of u to the minus 3. And so this is u to the minus 1 over 1 when I integrate. And this will be u to the minus 2 over minus 2 plus c. And so now replacing this is going to be minus x minus 2 to the minus 1 plus x minus 2 to the minus 2 over minus 2 plus c. And that'll be the end result for this integral. You can, of course, simplify the sign, but there's not much that you can do in there. Exercise 5 is this integral here where we have x over square root of 3 plus x squared. And again, the easiest substitution that we can do is just do u equals 3 plus x squared. And so the du is going to be, of course, 2x dx. And the u over 2 is just x dx. And so you can see that in the top, this is x dx. And here I have 1 over 3 plus x squared. So I can replace this part by the du, and I'm going to replace this part by the u. So that will be the integral of 1 over square root of u du. And so at this point, because I have limits of integration, then if x equals 1, then u is going to be equals to 4. And if x is equals 2, then u is equals to 7. 3 plus 2 squared, so 7 in there. So this is 4 to 7, and this is u to the 1/2 to the minus 1/2. Putting this up here so it can be seen as a power. And now I can integrate, and this is going to be u to the 1/2 over 1/2. using the powers plus c, if you will, and between 4 and 7. And so now here, the difference with sometimes before is that I don't need to go back to the original variable because I just replaced the limit of integration. So I can just plug in the limit of integrations and that's it. So this will be square root of 7, 2 square root of 7 plus c, then minus 2 square root of 4 plus c. And so c goes away with c, and this is just 2 factor out of a square root of 7 minus a square root of 4. Now, exercise 6, we want to evaluate e to the alpha, e to the ax, where a is a non-zero real number. So we have a substitution here as well. U is just equals ax, and the x is just going to be a. So then the u is just going to be a dx. But because we don't have that, then we can just write the u over 8 equals to the dx. So now the integral from e to the ax dx is equals to e to the u du over a equals 1 over a e to the u du. And this is 1 over a, and the antiderivative of e to the u is e to the u, so this is e to the u plus c. Since we don't have limits of integration, we go back to the original variable, and this is e to the ax plus c. Now for exercise 7, a little bit of operation is needed. So the best thing that you can do here is actually multiply things. So 1 by 1 minus e to the 3x is just 1 minus e to the 3x, and then when I multiply e to the 2x for this second part, I get e to the 2x minus e to the 2x times e to the 3x. Notice that this can be simplified as 1 e to the minus e to the 3x plus e to the 2x minus e to the, and then you can add this up because these are powers. So when you multiply powers, you cannot get to sum the exponents, and this is e to the 5x. In here is just a matter of obtaining the integral of each of the pieces. This is x minus 1 over 3 e to the 3x, 1 over 2 e to the 2x, and minus 1 over 5 e to the 5x plus c. Notice that this is the integral we found before, so we're using directly the result. Now for exercise 8, we're back to doing things that I can probably solve with a substitution. The problem here is this cube root of x plus 2. If it's just a cube root, it will be much more easier to manage. So this is why we're going to pick a substitution, u equals x plus 2. The du is going to be dx. And so, of course, because we see this x plus 1 here, then we're just going to see what u plus 2 being x means. That means that x plus 1 is actually going to be u minus 1. So this can be transformed into u minus 1 times a cube root of u du. And so this is much more simple now because I can put this in terms of powers. Remember that this will be u to the 1/3. So this will multiplying this by this will be u to the 1 plus 1/3 minus u to the 1/3. This will be the simplification of this. And so this will be u to the 4/3 minus u to the 1/3. And then integrating, we're going to add plus 1. So this is u to the 7/3 over 7/3 minus u to the 4/3 over 4/3 plus c. And I can see this as 3 over 7 u to the 7 over 3 minus 3 over 4 u to the 4 over 3. And then I come back to the original variable. And this is just going to be x plus 2. Here, and then we're coming back to the original variable as well. So now exercise 9 says that we should show the area between the x-axis of the function y equals log of x squared plus 1 between 1 and 2, and is going to be the same that the area of the function y equals 1/2 log of x between x equals 2 and 5. And we don't want to actually find the area according to this, so what we do is we're gonna organize this function. So let me just first introduce you to all the values of the function. The function that you see here is y equals x log of x squared plus 1 between 1 and 2. And so when you enclose this between 1 and 2, you can see that kind of like this looks like it's a triangle plus a square. You have this, let me just put an extra y equals 0.693. So when you create this line, you see that you have a square here on the bottom and that you have a triangle here. So this is 0.693 and the base is 1. So this is base 1 by 0.693. So this is going to provide me with this area. And now this triangle can be approximated by 3.21, which is this point, minus this. And so this is going to give me the height of this triangle by the base, which is 1. And so over 2. So that's going to give me that the total area of this is going to be 1.956. Closer to 2, but this is an approximation, remember. Now, if we introduce now the log between 2 and 5, you notice that we have this situation here. And again, we have another triangle that we can use to approximate this big part here. And we have a base that is a rectangle. So the rectangle can be approximated as 3, which is the base, by the height, which is 0.347. And then we can use the same base of 3 by the height, which will be the difference between this point here, which is 0.805 minus 0.347. And that's going to give me the height. So base by height over 2, and by the triangle before, it's going to give me 1.728. So the numbers are kind of getting close, not super equal. Probably is going to be much more precise if we really find what the area under the curve is. As you can see, the statement of those areas will be the integral between 1 and 2 of x log of x squared plus 1. And the second area statement would be from 2 to 5 of 1/2 log of x. Notice that this integral, you don't know how to integrate yet. You can probably try and do substitution, but you don't know what the integral of the log is. And you don't have the tools yet to do that, so I don't recommend to go further into this. Just with the approximation of the area by the triangle and the square is good enough to just kind of showcase they're the same. Now for exercise 10, we're going to see some change of variable to just transform these definite integrals. Here on the first one, u is going to be x squared plus 1. And so the du is 2x dx. You can see that the 2x dx is on the top. So this is going to be transformed into 1 over u squared du. And now we can transform the limits of integration. When x is equals 0, u is going to be equals 1. When x is equals 2, then u is going to be 5. Now I can integrate this, of course. This is u to the minus 2 du between 1 and 5. And that will be u to the minus 1 over minus 1 between 1 and 5. And this will be minus 1 over 5 plus 1. And that'll be the end result for this one. This is 5 over 5, so overall this is 4 over 5. For integral 2, we have the integral between 0 and pi over 4 sine square cosine of theta. So clearly the substitution here is u equals sine of theta. So that can get transformed into u squared. The du clearly is going to be the derivative of sine, which is cosine. And so this gets transformed into this. If sine of 0 is 0 and sine of pi over 4 is the square root of 2 over 2. So this gets to be those numbers. And then when we integrate, this is u to the 3 over 3 between 0 and a square root of 2 over 2. So we're essentially just plugging in a square root of 2 over 2 as a relevant factor. And this is going to be the end result in here. You can simplify that if you want to, but if you leave it in there, it's also good. Now, integral number 3 is going to be x squared e to the x cubed plus 1. So here u is x cubed plus 1 because we want to transform this into something of the shape e to the u, since it's much more easier to manage. Now, the u dx is, of course, going to be 3x squared. We have the x squared here, so we can say, well, 1/3 of the u is x squared dx. And then this gets to be 1/3 du. And now let's transform the limits of integration. When x is equals -1, then x cubed is going to be -1. This is going to become 0. Now with x is equals 2, x cubed is 8 plus 1, then is 9. And so this is the integral from 0 to 9 of e to the u. And so this is 1/3 e to the u between 0 and 9. And so that's going to be 1/3 e to the 9 minus 1/3 e to the 0 plus c. Okay, now number 4, we have the integral from 3 to 6 of 4x over x squared minus 4. Here, again, the substitution is u equals x squared minus 4. And then the du is going to be the 2x dx. Because we have a 4x here, we can just simply multiply 2 du, so we get the 4x dx. And so now we get to transform this into 1 over u times 2 du. And if x is equals 3, then u is going to be 9 minus 4, so it's going to be 5. And if x is equals 6, we have 36 minus 4, which is going to be 32. So simply the integral of this is 2 log of absolute value of u between 5 and 32. And this is just 2 log of 32 minus 2 log of 5. And if you want to, you can leave that in there. This is the end of that particular integral. Now, the next integral is going to be the integral from 0 to pi over 4 of sine of x over cosine cubed dx. Clearly, the problem is that cosine power to the 3 down there, so we're going to pick that as the substitution. If u is cosine of x there, then the du is going to be minus sine of x dx. And so transforming this will be, because we don't have the minus here, we're going to get a minus out. So we can get minus du. And this will be 1 over u cubed du. Now, if we plug with 0, x equals 0 is going to produce u equals cosine of 0, which is 1. And cosine of pi over 4 is the square root of 2 over 2, so that transforms this into these limits. Then this is like u to the minus 3, so I can simplify this as u to the minus 2 over minus 2 between 1 and the square root of 2 over 2. And so simplifying this is just 1/2 of square root of 2 over 2 power to the minus 2 minus and then in 1 here will be 1/2, and that'll be the end result for this. If you want to simplify it, you can do so as well. This is just pretty much powering everything to the 2 and flipping it around. So this will be 1/2, and this will be 4 divided by 2 minus 1/2. We simplify a little bit. This is 4 over 2 is 2. With this is 1. 1 minus 1/2 is just 1/2. And that'll be the end result for that integral. Now integral 6 is the integral from x 1 minus 16x squared. Again, the problem looks like it's going to be whatever is below complicating that root. So we're going to take that as the substitution. du is 1 minus 16x squared. du is going to be minus 32x dx. And so minus 1 over 32 du is going to be x dx, and that's going to be the transformation that we make. Since the x dx is the du, this is going to be essentially 1 over square root of u. And the u here, the transformation of the limits. When x is equals 0, we have that u is equals 1. And when x is equals 1 over 4, notice that x squared is 1 over 16, which cancel with the 16, it becomes 1. 1 minus 1 is 0. So this becomes the integral from 1 to 0 of 1 over square root of u, so which we can see as the integral from minus 0 to 1, flipping around the order of integration, of u to the minus 1 half. If I integrate this, is just u to the 1 half over 1 half between, with the minus here, between 0 and 1. And of course, this is just plugging into the 1 because here is going to produce a 0. And so this is minus 1. That'll be the end result for this integral. Now, integral 7 is the integral from 0 to ln of 4 of 2 e to the x over 1 plus e to the x. So here again, the problem is the denominator being complicated, so we're going to pick that as the substitution. U is equals 1 plus e to the x. The du is of course going to be e to the x dx, but because we have a 2 here, then we're going to multiply by 2, so we have those involved in there. This then is going to transform into 1 over u du, 2 du. So we're going to put the 2 outside. And if we plug in 0, this becomes e to the 0, 1. 1 plus 1 is 2. And if I plug log of 4, then e to the log of 4 becomes 4. So u becomes 5. So now the integral is twice log of absolute value of u between 2 and 5. And this is just 2 log of 5 minus 2 log of 2. And that is the end of integral 7. Now for exercise 11, we are checking now on areas. So first we want to find the area bounded by the graph of x squared plus 1 and y is equals x cubed. And the vertical lines x equals 1 and x equals probably minus 1. It has 2 1s, but that's probably a mistake. So let's take a look at those functions. So we make y, and I'm using Desmond's calculator here so I can simplify my calculations. And so let me make this between minus 1 and 1. And also x cubed. And so notice that between minus 1 and 1 is not like they're crossing each other. So I'm going to need to establish the boundary with the lines. So I'm going to do x equals 1, and I'm going to do x equals minus 1. So now I can see the area. The area that is being enclosed is this area in the middle here. That is the area that I'm calculating from the black line to the red line between the green on and the blue line. So when we're doing this, then notice that the function on top is x squared plus 1, and the function below is x cubed. That is important because when I'm calculating the areas, I need to define who's on top and who's on the bottom. So this is x squared plus 1 minus x cubed, the x. And now I can integrate. So this is pretty much x squared over 2 plus x minus x to the 4 over 4, and between minus 1 and 1. And so plugging in 1, this is 1/2 plus 1 minus 1 over 4. And plugging in minus 1, this is just going to be 1/2 minus 1 minus 1 over 4. So there are certain numbers that are going to cancel each other. This minus 1 over 4 is going to cancel with this one. This 1/2 is going to cancel with this one. However, notice that this 1 is going to survive, and is going to survive with this plus 1 here. So this whole area is going to be equals to 2. Now, a similar thing can be done for the second example here. Find the area bounded by the graph y equals x squared minus 2 and y equals x. So in this one, they're not giving me the limits of integration, so I gotta kind of find them out. And so I'm gonna do that graphically initially, and then I'm gonna show you how to do that by hand as well. So here y equals x squared minus 2 and y equals x. You can see that the points are in minus 1 and also in 2. So this is going to be set up as the integral of minus 1 to 2. And let's see who was on top. That is important. The function on top of the area that we're calculating is the line. As you can see, the line is on top, the parabola is below. So this is x minus x squared minus 2 dx. Now, if you want to find out where these two functions are equal, then you can set up y equals x squared minus 2 equals y equals x. And so this means that x squared minus 2 should be equals to x, and x squared minus x minus 2 should equal 0. And then you factor this out. Two numbers that multiply gives me minus 2. And then the sum gives you 1. So x minus 2, x plus 1. And so this is going to produce x equals 2 and x equals minus 1 here. Those are the two zeros that I get here. Now, this integral is x squared minus over 2 minus x cubed over 3, then plus 2x. This minus affect this between minus 1 and 2, and then you plug this is of course in 2. This is gonna be 4 over 2 is gonna be 2 minus a over 3 plus 4 minus, and then you plug now minus 1. It's gonna be 1/2, and then minus plugging here is gonna pull out the minus, so minus 1 over 3, and then minus 2. Let's see. I can kind of add them up, some of these numbers. 2 minus 1/2. I can see this as 4/2. So 4 minus 1/2 is 3/2. So I got this one and this one. This minus a over 3 minus 1/3 is minus 9 over 3, which is minus 3. So minus 3. And then 4 minus minus 2 is just going to be plus 6. So at the very end, this is just like 3/2 plus 3. And this can be a 6/2. And so overall it's 9/2 the total area. Now, the last exercise of the worksheet is find the area region bounded by the graph between x equals x cubed and x. Again, you can do that by graphical means. And you can see that is this. And you cannot see that is between minus 1 and 1, but it's flipping around who's on top. So from minus 1 to 0, we have that the x cubed is on top, and from 0 to 1, you have that x is on top. So to find the area here, you gotta be very careful because it's gonna be split in 2. It's gonna be x cubed minus x, and then plus from 0 to 1 of x minus x cubed. Super important why understanding the graphical part, so because it tells you who's on top, and that's going to change the whole result. Notice over here I'm going to get x to the 4 over 4 minus x squared over 2 plus, and then here I'm going to get x squared over 2. Sorry, this is between minus 1 and 0. And this one here is x squared over 2 minus x to the 4 over 4 between 0 and 1. Now, if I plug my numbers here in 0, obviously this is going to be 0. So it's only matter of minus 1. And so I'm going to have a minus, and then plug in a minus 1. I have 1 over 4 minus 1/2. Which is clearly going to be minus 1/2. So with the minus here is just 1/2. And then plus. And then if I plug in here, it's clearly just 1/2 minus 1 over 4. So it's going to be another 1/2. And the whole sum is going to be 1. If you are mistaken for some reason, and you just do the integral from minus 1 to 1 of this, you might get a 0. So if you're not careful, you might get an area null where you actually have an area.